A car's operation is largely dependent on the engine's ability to generate power and transfer it effectively to the wheels. The power generated by the engine is converted into torque, which is the rotational force that makes the vehicle move. However, the amount of torque produced by the engine alone is not always sufficient to move the vehicle, particularly when starting from a standstill or when extra force is required for acceleration. To address this, the torque needs to be increased, and this is done through the car's transmission system. Torque amplification is achieved by adjusting the gear ratio. The basic principle is that the lower the PM revolutions per minute of the gears, the greater the torque output. In the transmission system, engine torque is altered by changing the PM either by increasing or decreasing it. This is done by shifting gears, where smaller gears mesh with larger ones. A smaller driving gear turning a larger driven gear results in a lower rotational speed for the larger gear but provides more torque. This increase in torque is crucial for tasks such as accelerating from a stop or driving uphill, for the engine to transmit its power to the transmission system effectively. A connection must be established between the engine and the gears. This connection can be temporarily disengaged when needed, which is the function of the clutch. The clutch allows the driver to disconnect the engine from the transmission in order to change gears smoothly. When the driver releases the clutch pedal, the engine power is transmitted to the input shaft, which then drives the wheels. Pressing the clutch pedal, on the other hand, disengages the engine from the input shaft, allowing for a gear change without grinding or damaging the gears. The gear ratios in a vehicle are carefully designed to ensure that the engine operates at an optimal PM across different driving conditions. The transmission system adjusts the gear ratio to balance the engine's PM with the required torque and speed of the vehicle. For example, in lower gears, higher torque is necessary, especially when the car is starting or climbing a hill, whereas in higher gears, less torque but more speed is needed for efficient highway driving. To make shifting gears smooth and to avoid noise or damage, the gears must rotate at the same speed before they mesh. This is where the synchronizer comes into play. A synchronizer ring is a component that ensures the gears are rotating at the same speed before they engage. It uses friction and a specially designed surface with sloping edges to equalize the rotational speed between two gears. This synchronization process prevents the unpleasant grinding sound that occurs when gears of differing speeds attempt to mesh, and ensures a smooth, silent transition from one gear to another. In synchronized transmission systems, all gears are constantly in mesh, but they are not all engaged at once. While the gears on the countershaft are fixed in position, the gears on the output shaft rotate on their own bearings. When a driver shifts gears, the current gear is locked to the output shaft using a linkage and sleeve mechanism. This locking process allows the engine's power to pass through the selected gear, transmitting the drive to the wheels. To start the vehicle from a stop, the driver engages first gear. First gear has the highest gear ratio because it pairs the smallest driving gear on the countershaft with the largest driven gear on the output shaft. This creates a significant torque increase, which is necessary for overcoming the inertia of the stationary vehicle. As the car accelerates and reaches a higher speed, less torque is needed, so the driver shifts to a higher gear with a lower gear ratio. In second gear, the sleeve locks the second gear onto the output shaft, allowing power to pass through it. The ratio between the driving and driven gears is smaller in second gear than in first, resulting in higher speed but lower torque. The process continues in higher gears, with the gear ratios getting smaller as the driving and driven gears become closer in size. In third gear, the sleeve locks the third gear to the output shaft, and the drive is transmitted through both the third gear on the countershaft and the third gear on the output shaft. This further increases the vehicle's speed, while simultaneously decreasing the torque available for acceleration. By the time the vehicle reaches fourth gear, the transmission system allows for even greater speed, but with significantly reduced torque. In this gear, the power is transmitted directly from the engine's input shaft to the output shaft without involving any gears in the process. This is known as direct drive, where the PM of the engine matches the PM of the output shaft. Since there is no need for torque multiplication at high speeds, direct drive is more efficient and provides a smoother ride with less mechanical complexity. When the driver engages reverse gear, an additional gear is introduced into the system between the last gear on the countershaft and the output shaft. This additional gear changes the rotational direction of the output shaft, causing the vehicle to move backward. The introduction of reverse gear highlights the versatility of the transmission system, allowing the vehicle to move in both forward and reverse directions by changing the gear arrangement. Understanding the interaction between gears is crucial for efficient driving. In lower gears, such as first or second, the vehicle is slower but produces more torque, allowing it to pull harder, which is useful for accelerating from a stop or climbing hills. In higher gears, the vehicle can travel at faster speeds with greater fuel efficiency, but the available torque is lower, which means acceleration is weaker. Adjusting gears appropriately based on driving conditions ensures the vehicle performs optimally. balancing speed, power, and fuel consumption. The careful engineering of the transmission system allows drivers to navigate a wide range of conditions, from city streets to highways, while maintaining control over the vehicle's power and performance. In essence, the transmission system is a finely tuned mechanism that optimizes the engine's power output to match the demands of different driving conditions. By regulating the torque and speed through gear ratios, drivers can maintain control over the vehicle's performance, whether it's for acceleration, climbing, or cruising. Each gear serves a specific purpose, with lower gears maximizing torque and higher gears enhancing speed and efficiency. Proper utilization of the transmission ensures smooth operation, reduced wear on the engine, and better fuel economy, making it a critical component in modern automotive engineering. Moreover, advancements in transmission technology, such as dual-clutch systems and continuously variable transmission (CVTs), further refine the balance between power, efficiency, and driving experience. Catering to diverse vehicle needs from performance sports cars to fuel-efficient city commuters.